Hey again, we're back and we're going to be starting Unit 2, which is equilibriums.
Okay, so an equilibrium reaction is a reaction that is reversible. That means it can go forward and backwards
At the same time. So when the rate of the forward reaction is equal to the rate of the reverse reaction is called an equilibrium. So what that means is that during the forward reaction, when a forward reaction is happening, a reverse reaction is happening at the exact same time. So if you have a very simple equation like A is turning into B plus C, what that means is as A is turning into B and C are combining and turning into A. Okay, so yeah, there's a forward reaction of A going into B and C, or in other words, a decomposition reaction going forward, and then a synthesis reaction going in the reverse way. So a reaction going this way and this way. Now, when the forward reaction is moving at the same rate as the reverse reaction, that is when it's called an equilibrium. So say again, let's take this example of A turning into B plus C. If A is turning into B plus C faster than B and C combining and turning into A, then it's not at equilibrium. The rates have to be equal. The forward reaction rate has to be equal to the reverse reaction rate to be in equilibrium. And if the rates are equal, the concentration of the reactants is going to stay constant, and the concentration of the products are going to stay constant. So if we were to graph something like this, so let's graph A turning into B plus C. So let's say we start with a whole bunch of A, because A is our reactant. So we start with a whole bunch of A, and then we have B and C. Now I'm just going to write B here instead, and I won't bother writing C. So say if we start with a whole bunch of B and we start with start with a whole bunch of A and start with 0 B, then B is down here and A is up here. So what's going to happen is, as the forward reaction happens, the concentration of A starts to decrease. And as the forward reaction happens, the concentration of B starts to increase. Now, as the concentration of A starts to decrease, then there's less of it to react, and it starts to level out. And since it starts to level out, B also starts to level out. And what we see here is that the concentration of the reactants, or the concentration of A, becomes constant, becomes a flat line, and the concentration of B also becomes a flat line. So what we would say is, at this point right here, this here is at equilibrium. This is not at equilibrium. So the reactants are constant and the products are constant. Okay? And also the forward of the rate and the reverse rate of the reactions do not change. Or in other words, the forward rate and the reverse rate are equal. Now, a lot of people get confused on this part. They think at equilibrium the concentration of the reactants have to equal the concentration of products. That's not true. The concentration of the reactants, which is A right here, does not have to equal the concentration of the products. Okay? Just the rate of reaction has to equal each other. Now, a few other notes that we have here is temperature can affect an equilibrium. So these can shift and change based on temperature, whether it be exothermic and endothermic, and we'll talk about that later. Now, new equilibriums are attained at new temperatures. So say if there's a temperature change, something might change here, and it could move up or it could move down, but what could happen is that if this moves up and then maybe this one moves down, but what eventually happens is that a new equilibrium will happen. So at this point, this is not at equilibrium, and this again is at equilibrium because it's nice and flat here. So this would be the concentrations of. Now, all of the equilibriums that we talk about here are what we refer to as dynamic equilibriums. So macroscopically, you cannot see any changes. Microscopically, the forward and reverse reactions are constantly happening. So what does macroscopically mean? It means during an equilibrium right here, it looks like nothing is happening, or during an equilibrium right here, nothing is happening. So that's what macroscopically, what you can see with your with the naked eye, nothing is happening here. But microscopically, particles are constantly moving, and particles are constantly going from reactants into products, and particles are constantly going from products into reactants. So microscopically, they're moving a lot. Now, here, again, here is not an equilibrium. This is not an equilibrium. Now, what is a spontaneous reaction? Well, a spontaneous reaction is a reaction which occurs by itself without any outside assistance. Usually spontaneous reactions want to lose energy and become more stable. By having less potential energy, they become more stable. So let's take a look at an endothermic reaction right here. So a more stable reaction, a more stable state is something that has less potential energy. Okay, so the reactants here have less potential energy, and therefore this reaction will kind of move in this way. The reverse reaction will be favored. In other words, the forward reaction would not be spontaneous. So again, what we call this is reactions favor minimum enthalpy. In other words, reactions want to move in the direction with the lowest potential energy. Okay, so here, this is an exothermic reaction. So here's an exothermic reaction. And since this is, the reaction wants to move spontaneous. This is a spontaneous reaction. Because the reactants start with about 40 kilojoules of energy, and they move down to about 20 kilojoules of energy. So the reactions usually favor the minimum amount of enthalpy. C and D have an enthalpy that is about 20, and A and B have an enthalpy of 40. So in an exothermic reaction, the products are favored. So exothermic reaction, we'll write products favored, and that means this one is going to be spontaneous in the forward way. Now this one, the reactants have a lower enthalpy, and therefore the one that is favored, okay, the reactants are favored because they have lower enthalpy. So reactions always favor, reactions favor minimum enthalpy. Now we're going to talk a little about the other force that drives reactions, and that is entropy. Now entropy is the amount of randomness in a system, or in other words, some refer it to a little bit as like a chaos kind of idea. So what I have here is a sample of maybe sodium chloride and dissolving in water. So here's a water molecule right here, and here's maybe a sodium chloride, so this would be a Cl, and this would be an Na. Now, this block right here is solid NaCl. Now, over here, this is dissolved, okay, or Cl ions, and this would be an Na plus ion. So it's slowly dissolving in water. Now, what we have to figure out is, how does a salt that is solid dissolve? Well, let's think about this right here. So this salt, or this Cl minus, used to be right here. It used to be right about there. Now we have to figure out when a water molecule attaches to this chlorine molecule, chlorine ion. We have to figure out what possible directions can this chlorine go. So one possible direction is that the way that it shows in this picture, it can go this way. Another possible direction is it can go this way, or this way, or this way, or this way, or it can even go this way, or this way. In other words, what I'm showing right here is that the chlorine ion could go in pretty much very, very close to infinite different ways, in infinite different directions it can go. So this chlorine ion, chlorine can go in an infinite different directions, and one direction it can go is one way it can stay. So there's one possibility where the chlorine ion does not move, so no move. So if I were to make a little chart right here, so chance, okay, so there's one chance that this chlorine ion no move, okay, so I'll write here direction. Now, there's one chance that the chlorine ion will move in this direction, and there's another chance, one chance, that'll move in this direction. And if I add up all these chances, just move in any direction, well, it's a really big number, a really, really, really big number. So in other words, there's one chance it'll stay there, and pretty much an infinite other chances it'll move. So if I was a betting person, I would probably bet that chlorine would move in one of any of these directions, and probably not stay where it is. And now same with this one. This also has one chance of staying where it is. All of these have one chance of staying where it is. But that one chance, that one over infinite different possibilities, is such a small number, well, that it's pretty much 0%. Like 1 over infinity is just a very, very small number, and that means that this is probably going to dissolve, especially when the chances of this one is 1 over infinity, and the chances of this one's 1 over infinity, and the chances of this one's of 1 over infinity, and same of this one. So we're looking at a very, very small chance that this solid NaCl will stay a solid NaCl. And this whole process, this chance, is called entropy. That it is more likely for it to move in any direction than to stay in the same location. And that chance, that randomness, causes this to dissolve. So let's look at another example of entropy here, try to explain it. So let's pretend we have something like this, which is let's pretend this is a glass ball, and we give it a little bit of energy and we drop the glass ball. Now, there's a chance that this piece of the glass stays exactly where it was, but there are more chances for this piece of glass right here to move in this direction, or in this direction, and you get the idea. This is it can move in a lot of different directions. And so when this glass ball is given some energy and it's dropped, well, all of them usually move all in other places. And this has what we call more disorder. This scenario has more disorder, and therefore this has higher entropy. So this is high entropy. And this is highly ordered, or in other words, it probably took a lot of energy putting all of those things nice and neatly together. And this did not happen by accident. All these pieces of glass put together and made into a perfect ball right here. This wasn't by accident. This took a lot of order, a lot of energy, and it did not happen randomly. Okay, so this has what we say low randomness, or in other words, low entropy. It's very, very unlikely that this happened by chaos or by chance. Now, let's talk about these kind of things. So, things like gases have a lot of randomness, and as we move into this direction, we see solids, which are very, very orderly. Now, that means they have low entropy. So here is again high entropy, or high amount of randomness, and this is low randomness, or low entropy. Now, if you think about this, here is in a gas, when you have molecules, you have a couple molecules of gas, and they're just moving around so much, and they have a lot of energy, and they're moving around, and they have a lot of randomness. Those molecules are going to be moving around so much. Now, when you have a solid, though, the molecules are so nicely close together that these molecules are not going to be moving around that much. They're going to be always sticking together and staying together, and therefore they have a lot of order. It took a lot of energy to put them in here, not a lot of randomness there. So maximum entropy, so gases have a lot of entropy, and solids have a lot. And so let's look at a reaction right now. So which side would be favored? Would this be a spontaneous reaction when you consider entropy? So solid and a liquid, and a gas and a gas. So since these two gases have more randomness, this is an increase in entropy. So this one, C and D, have high entropy. Okay, because it has lots of gas and gas, and now this is solid and liquid. This has what we call low entropy. Low entropy, or in other words, high order. This has a lot of order right here. Now, looking at another example, we have magnesium solid plus hydrochloric acid, which is aqueous. So we have an aqueous and a solid making a gas and aqueous. So high entropy, this is a spontaneous reaction that would favor the products. So reactions favor maximum entropy and minimum enthalpy. Now let's move on. And another thing is that this maximum entropy is determined by what phase is it in. Okay, so gas, aqueous, liquid, or solid. Now, if we take a look at the another thing too is that we need to think when we talk about maximum randomness or maximum entropy is the number of particles. The more particles, the greater the entropy. Think of it like this way. Say if you have a glass cup or a glass beaker. So we have a nice beaker right here. Okay, and what we see is that if I were to take this beaker and drop it onto the ground, what would happen to this beaker? Well, the most likely scenario, what is going to happen to this beaker is that it's going to break into lots and lots and lots of pieces. Okay? It's very, very unlikely that it's going to break into less pieces. Because and that's the same thing for reactions. When reactions happen, it is more likely, it is more random for things to break into many pieces than things to break into less pieces. So what we see here is reactants A plus B going into 2C plus D. So in other words, we have one particle plus another particle, so one particle plus another particle, or in other words, two particles, and they are reacting to make 2 plus 1, 3 particles. So again, 2 particles breaking into 3 particles. This is going to favor the products, and this has a higher number of particles means a higher amount of randomness. So this is high entropy. Okay, let's take a look at this last slide right here. So what we see here is an example of what we have is a sugar plus oxygen making CO2 and H2O. Now, this is a exothermic reaction because this is a combustion reaction. So therefore the delta H is going to be negative. Okay, so delta H is negative here. And this is going from a solid and a gas to a gas and a liquid. Okay, so therefore the S, or entropy, or the amount of randomness, is increasing. So what we see here for the first one is minimum enthalpy and maximum entropy. And therefore, is it spontaneous? Yes, it has everything pushing the reaction forward. So this first one right here, again, has enthalpy, it has minimum enthalpy. It's exothermic. So minimum enthalpy is pushing it forward. The exothermic, so it's favoring the products. Okay, so minimum enthalpy is favoring products. Maximum entropy is also favoring products. So this reaction is spontaneous, it's going forward. Now let's look at the second one. We have a liquid going into a solid. Okay, so randomness, no, the randomness is not increasing. So what we see here, the randomness is decreasing. A liquid going into solid, we're decreasing our randomness. However, a liquid going into a solid means that it has to lose a lot of energy in order to become a solid. Okay, so it has to lose a bunch of energy in order to become a solid, and therefore it's going to have a delta H that is negative. So can this reaction be spontaneous? And the answer is yes. One of the forces is pushing it forward. So randomness is pushing it towards reactant side, but minimum enthalpy is pushing it towards product side. So it is possible that this can be spontaneous. Now for the next one right here, we have the exact opposite reaction. We have a solid going into a liquid. Now, a solid going into a liquid, that means the amount of randomness is increasing. However, the amount of, now since this is absorbing energy, the change in enthalpy is increasing. So this is not. Okay? So this is not pushing it towards products. So again, everything here, this is pushing it towards products. This is not pushing it towards products, and this is also not pushing it towards products. Okay, we'll circle those ones in blue. Okay, so again, products, 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 and the blue ones are pushing towards reactants. So now we have CO2 plus H2O making sugar and oxygen. Well, this is the same reaction that plants do. Plants absorb water and CO2 to make sugar, and they have to absorb a lot of energy. They absorb a lot of energy in the form of sunlight. So since they're absorbing a lot of energy, they have a delta H that is positive. And also too, we have a gas and a liquid becoming a gas and a solid. And that means our randomness is not increasing, our randomness is decreasing. And so therefore, is this spontaneous? No. Everything is pushing here towards the reactant side. Okay. Now, I have a little bit of a description here of what delta H is and delta S, and kind of explains these things, and you can read through that there.